Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And today's lecture, we will be seeing necessity of series connection of SCRs, what are the problems encountered with series connection, static equalization and dynamic equalization. And firstly, what is the necessity? Why we need to actually go for series connection of SCRs? Let me give you an example. If I need to operate the string of 1000 volts, in that case, I have SCR of rating only 500 volts. In that case, if I apply this particular thyristor to 1000 volts, it may get damaged because of the high voltage which we are applying. So that is the reason what I do is I take SCR of another 500 volts and then connect it in series such that I can increase the voltage rating of the SCR and thereby my SCRs will be safely operated. So in order to increase the voltage rating, we will be going for series connection. And you may ask me a question, why not we take a single thyristor of 1000 volts and operate? We can take, but in HVDC, the requirement will be sometimes it will be 5 kilovolts. At other times, it may be 10 kilovolts. And some other time, it may be 15 kilovolts. For each rating, we cannot manufacture different thyristor, separate thyristor every time, which is difficult and it also increases the cost. So that is the reason in order to meet a string requirement, we will be connecting the SCRs in series and thereby increase the voltage rating of the string. And here, what are the problems encountered with series connection? Yeah, we have connected two SCRs of same rating in series and we have operated. But what will be the problems encountered if such SCRs are connected in series? We might think these two SCRs are of same rating, but there will be certain difference in their internal characteristics, which includes forward breakover voltage of the thyristor. Let me show you here. See, this is the forward breakover voltage of say thyristor 1 and this is the forward breakover voltage of say thyristor 2. And there is a difference in forward breakover voltage of thyristor 1 and thyristor 2, though these two are of same rating. So this is the problem associated. Likewise, we have difference in internal resistances and internal leakage currents. Leakage current of both the SCR might also be different, though we have considered the SCRs are of same rate. So these are one of the problems which are encountered. And the other problem is voltage appears across the SCR, which turns off late. High voltage will be appeared across the SCR, which turns off late. And this is due to the difference in dynamic characteristics of the SCR during turn-off time. Say this is the turn-off time of thyristor 1 and this is the thyristor 2 turn-off time. And there is a difference in turn-off time of both the SCRs, though both are of same rate. So these are the two problems which have been encountered. And here, see, for the reason 1, that is due to the difference in internal characteristics, let me give you an example. Like I have considered the thyristor 1 and thyristor 2, these two connected in series, and if you see, the internal resistance of thyristor 1 is very high when compared to that of thyristor 2. In that, see, it ultimately depends. If the internal resistance is high, in that case, the leakage current across this particular SCR will be less. If internal resistance is high, leakage current will be less and thereby the voltage which is appeared across the SCR will be more. That means it blocks more forward voltage. T1 is blocking more forward voltage when compared to that of T2. So it may damage the T1 and it should not be happened. For that purpose, the solution is we will be going for the static equalization circuit. In static equalization circuit, what we do is, see, if say thyristor 1 has high internal resistance and in that case the leakage current will be less and high voltage will be appeared across the thyristor 1, and it may ultimately damage the thyristor 1. It should not be happened. So I have considered the same example as that of the previous case. If you see, thyristor 1 resistance is 1000 ohms, whereas thyristor 2 internal resistance is 700 ohms. And in order to mitigate this, I am considering the resistance X in parallel to that of thyristor 1, such that if you calculate the equivalent resistance of these two resistances which are connected in parallel, that is given by 1 by X plus 1 by 1000, and we'll select the value of X such that the equivalent resistance will be equal to that of 700 ohms, equal to that of the resistance of thyristor 2. Thereby, we are actually balancing the value of the resistance which is connected across the string. And here, see, for each thyristor, manufacturing the resistance which is suitable for the thyristor will be difficult. So, we'll be manufacturing one value of the resistor such that the static equalization is successfully achieved. For that purpose, here we are doing a derivation, and let me consider the current flowing through this particular thyristor 1 is the leakage current of the thyristor 1 is denoted with ID1, and the current flowing through this particular resistance is I1, and the voltage across the thyristor 1 is VD1. And what I have said, the internal resistance, let us assume the internal resistance of thyristor 1 is high when compared to that of N-1 SCRs. So here the leakage current which is flowing through thyristor 2 is ID2, and current flowing through resistance is I2, and the voltage across this particular thyristor 2 is VD2. And here I am applying, let me apply KCL across this at this particular point, say A. Applying KCL at point A, we get, see, algebraic sum of incoming currents is equal to algebraic sum of outgoing currents. In that case, ID1 plus I1 is equal to ID2 plus I2. And let me find out the value of I2, which is equal to I1 plus ID1 minus ID2. See here, I1 minus, let me take minus common here, ID2 minus ID1. In that case, we get I2 is equal to I1 minus delta ID. This is I2. Say this is equation 1. And now, let me apply KVL for this particular string. In that case, total voltage Vs across the string is equal to I1 into R plus I2 into R into N-1 SCS. That is, the internal resistance of thyristor 1 is high when compared to that of N-1 SCS. So that is the reason I have considered like this. And now, in this particular equation, let me substitute equation 1. I get I1 into R plus I2 is nothing but I1 minus delta ID into R. In that case, I get I1 into R plus, let me simplify this, I get N into I1 R minus N into delta ID into R minus I1 into R, minus of minus plus delta ID into R. So this is nothing but your Vs. Let me rewrite this equation. I get Vs is equal to, let me substitute in place of I1R is equal to VD1 plus N into VD1 minus N into delta ID into R minus This is I1 into R minus I1 into R. Again, I am writing it as VD1 plus delta ID into R. Here, VD1 gets cancelled, and the resultant equation will be N into VD1 minus delta ID into R. If I take common, in that case, N minus 1 I get. This is nothing but Vs, and I need the value of VD1, voltage across the thyristor 1. In that case, the equation transforms into Vs plus delta ID into R N minus 1 by N. This is the required equation, that is VD1. And other thing which I need is that equivalent value of the resistance which should be connected across the whole string. So here R is equal to the value of the equivalent resistance. R is equal to NVD1 minus Vs by delta ID into N minus 1. This is the value of the required value of the resistance which should be connected across the whole string such that static equalization can be achieved. So here in dynamic equalization, because of the turn-off times, difference in turn-off times, though we consider the same value of the SCRs, all the SCRs in forward blocking state, turn-on and turn-off times differ. And that is difference in dynamic properties due to difference in junction capacitances offered by the individual SCR. That is, whenever the SCR in forward blocking state, junction J2 forms as a capacitance, junction capacitance. So high voltage appears across the SCR which turns off late. So that is the reason capacitor 1 provides equalization during turn on and turn off. R1, this is used to limit the discharge current. That is, what am I saying is, see, because the turn off time of both the SCRs may not be one and the same. So that is the reason that in order to neutralize this junction capacitance, we connect the external capacitance across this particular thyristor such a way that if the excess voltage is applied across the thyristor due to the difference in turn on and turn off time, that is, say if the whole string is turning off at a particular instant whereas T1 is still not off, so in that state the high voltage will be appeared across the T1 and this thyristor 1 may get damaged, and it should not be happen. So that is the reason what we do is, in order to neutralize this junction capacitance, we connect the capacitance across the thyristor such a way that whenever the high voltage, that is dV by dt occurs, or high voltage is applied across the thyristor, in that case what happens is this capacitor starts charging and thereby protecting the thyristor from the high voltage. And if you see here, not just capacitor, in some cases this resistance is actually connected in series with the capacitance, and here we are actually connecting the diode in parallel with that of the capacitor so that the charge time of the capacitor will be getting reduced. It is because if this capacitor is getting charged through the resistance, in that case the time constant tau is equal to, it becomes RC. The time constant will be getting increased, and that should not be happen. So that is the only reason, in order to reduce the time constant of the capacitor, we are connecting the diode across this particular RC combination such that whenever high voltage is applied across the circuit, in that case it gets charged through this diode and then back to capacitor. And once the capacitor is completely charged, at that instant this diode will be getting reverse biased because of the polarity of capacitance, and this resistance provides the discharge path for the thyristor, and this capacitor gets discharged through the resistance so that SCR will be protected from the discharge current. So in order to reduce the difference in turn-off time, in order to protect the thyristor from high voltage, we are actually connecting this capacitor. And this is also nothing but the same funda will be used in stubber circuits as well. So this protects the thyristor from dV by dt high voltage, as well as it also protects the thyristor from it also acts as a stubber circuit. So what is the value of the capacitance which should be connected across the SCR in order to provide the dynamic equalization? So for that purpose, let me consider the equation VD1 again. VD1 is equal to Vs plus n minus 1 into delta ID into R divided by n. This is VD1. And here, what am I doing is, in this equation, in place of delta ID, I am writing it as delta V by N. And here, you all know very well where V is equal to, from basic formulas, V is equal to Q by C. In that case, we can write this as delta V is equal to delta Q by C. Yes. Let me substitute this delta V in the above equation. I get VD1 is equal to Vs plus n minus 1 into delta Q by C1 by n. And here I need to obtain the value of that capacitance which can be connected across all the SCRs so that I can provide the dynamic equalization. So in that case, I get n into VD1 minus Vs is equal to n minus 1 into delta Q by C1. So here that value of C1 is equal to n minus 1 into delta Q divided by n into VD1 minus Vs. This is the value of that capacitance which is to be connected across this whole string so that dynamic equalization can be achieved. And then here are some formulas. If number of SCRs are connected in series, in that case, string efficiency is nothing but the rate at which each SCR in the string is being utilized. And that is given by the formula actual voltage rating of the SCR divided by N into actual voltage of each SCR. And then if SCRs are connected in parallel, in that case, string efficiency, it is given by actual current rating of the string divided by N into actual current rating of each SCR. Similarly, derating factor, it is given by 1 minus string efficiency. And here, derating factor, it is nothing but the measure of reliability of the string. And it is given by percentage D is equal to 1 minus Vs by N into VD1 into 100. And string efficiency, as I already told you, the amount by which each SCR in the string is utilized. And it is given by string efficiency is equal to 1 minus derating factor into 100.